Hello, welcome to the last paper of my session that is going to be presented by Farzana Ahamed Bhuiyan and is called Practitioner Perception of Vulnerability Discovery Strategies and is authored by Farzana from Tennessee Tech University, Justin Murphy, Patrick Morrison from IBM, and Akond Rahman also from Tennessee Tech University. And now, Farzana, the floor is yours.
Thank you. Hello everyone. I'm Farzana Ahmed Bhuiyan, a fourth year PhD student in Tennessee Tech University. Welcome to our presentation titled Perception of Vulnerability Discovery Strategies. This work is in collaboration with Justin Murphy and Akond Rahman from Tennessee Tech University and Patrick Morrison from IBM. So, what is a vulnerability? Vulnerability is a weakness in the computational logic found in software and hardware components that, when exploited, may result in impact to confidentiality, integrity, or availability. All vulnerabilities in the National Vulnerability Database or NVD has been assigned a CV identifier, and thus they all abide by this definition. Vulnerability discovery is a human-centric activity where the security tester applies security knowledge to identify vulnerabilities. On online forums such as Reddit, we observe practitioners ask about strategies that security testers perform. Moreover, many IT organizations may not have the expertise of security testers, which potentially prohibit them to identify latent vulnerabilities in their software. Therefore, a systematic synthesis of the vulnerability discovery strategies can help practitioners in identifying the latent vulnerabilities. In our previous work, we identified 4 vulnerability discovery strategies that can help practitioners in identifying the latent software vulnerabilities. We also reported the frequency of the identified discovery strategies. One limitation of our prior work was validation with practitioners. We did not synthesize practitioners' perceptions of the identified strategies. Addressing such limitation is important, as practitioner agreement with the identified strategies can provide validation and evidence of usefulness for the identified strategies. Similarly, practitioners' disagreement can reveal for which reasons the identified strategies may not work. We answer the following research question. How do practitioners perceive the identified vulnerability discovery strategies? First, let's have a look at each of the 4 categories. The first category is diagnostics. This is the strategy of inspecting software source code or software logs to discover vulnerabilities. During the inspection process, the security tester apply their knowledge and inspect for patterns that are indicative of security weaknesses in the software. This strategy includes 2 subcategories: diagnosis of software source code and diagnosis of software logs. When diagnosing source code, security testers search for security weaknesses such as insecure coding patterns and incorrect implementations of cryptographic algorithms. And in the logs, security testers inspect evidence of vulnerabilities such as information leakage and uninitialized memory access. The second strategy is malicious payload construction. This is the strategy of constructing a malicious software artifact to discover a vulnerability. For this strategy, security testers construct the payload with code snippets or binary files. Upon construction, the payload is passed as input to the software, which may lead to an undesired consequence, such as software crashes or leakage of data. We observe two subcategories for this strategy. First one is the construction of malicious code snippets, which is done either manually or using automated tools such as fuzzing. And the second one is constructing malicious binary files such as certificates, that mean data files that digitally bind a cryptographic key, document such as PDF files, multimedia files such as image and video files, and finally executables such as .exe files. Third category is misconfiguration, which is the strategy of identifying and altering one or multiple configurations of the software to discover vulnerabilities. As part of this strategy, security testers first identify the software's configurations values. Then testers alter the configuration values to discover any potential vulnerabilities. The fourth and the last category is pernicious execution. This is the strategy of identifying a sequence of software interactions that expose a vulnerability. While an end user interacts with a software to accomplish a certain task, a security tester interacts with the software to discover vulnerabilities. For example, using this category, security testers may find vulnerabilities that occur due to race conditions. The difference between pernicious execution to the other strategies are, unlike diagnostics, the practitioner does not inspect source code and build or debug logs. Unlike malicious payload construction, here practitioner does not create malicious payload and pass it as input to the software project of interest. And finally, unlike misconfiguration, here the software's configurations are not altered. Now, using the probe vulnerability metric, we quantify the proportion of vulnerabilities that are identified using each strategy. Here the column diagnostic stands for diagnostics, execution stands for pernicious execution, misconfig presents misconfiguration, and finally the payload presents malicious payload construction. We could see that except for Eclipse and OpenStack, payload construction is the most frequent vulnerability discovery strategy. For Chrome, Firefox, and PHP, 83% or more of the total vulnerabilities are discovered using malicious payload construction. And for Eclipse and OpenStack, the most frequently occurring strategy is diagnostics. For Eclipse, 62.9%, and for OpenStack, 52.1% of vulnerabilities are discovered using diagnostics. We answer our research question by conducting an online survey with practitioners. In the survey, we first asked practitioners about their experience in software engineering. Next, we asked how long they have been involved in discovering vulnerabilities in software projects. We also asked to which extent do they agree that each of our strategies could help them to identify an undiscovered vulnerability. We used the Likert scale to measure agreement levels. It has 5 levels: strongly disagree, neutral, agree, and strongly agree. We also add an open-ended text box so that the survey respondents can provide more context, including feedback on the reasons they agreed or disagreed. We deploy the survey using emails. We use two sources. First, we use a mailing list maintained by a university-affiliated organization which is involved in vulnerability finding initiatives, such as Capture the Flag. And second, we collect email addresses from our collection of bug reports from Chrome, Eclipse, OpenStack, and PHP. We select 300 email addresses, 30 email addresses from the university affiliated mailing list, and 270 email addresses from the OSS bug reports. Of the 300 practitioners, 51 practitioners responded to the survey. We observed the median reported experience in software engineering to be 4 years and a median of 2 years of experience in vulnerability discovery. We summarize our survey result in this figure, where the strategies are sorted from top to bottom based on the agreement rate. The survey respondents who agreed or strongly agreed with each category is listed on the right. The agreement rate is 88% for diagnostics, 80% for misconfiguration, 76% for malicious payload construction, and 75% for pernicious execution. The survey respondents also provided comments on why they agreed, disagreed, or remained neutral. One survey respondent agreed with all the identified strategies, stating that I have seen all of them work before and they are effective at finding vulnerabilities. One respondent expressed a lack of experience in malicious payload construction, saying, I don't know how much impact a malicious payload has, but it sounds like it's important, so I put neutral. One respondent disagreed with malicious payload construction, stating that the strategy is situationally beneficial. The respondent perceived the success of finding vulnerabilities using malicious payload construction to be dependent on developers' mistake in source code. And another respondent suggested that other strategies may exist, which are not included in our list, saying that there may be more strategies added as we go on identifying more and more severe. To conclude, our work provides evidence that practitioners who are interested in early discovery of vulnerabilities can leverage the 4 strategies to identify latent vulnerabilities. From our survey, the most and least agreed upon strategy is respectively diagnostics and pernicious execution. In short, we talked about the vulnerability discovery strategies used by security testers in open source software and the frequency of the identified vulnerability discovery strategies. We showed evidence that practitioners can leverage the 4 strategies to identify latent vulnerabilities. From our survey, the most agreed upon strategy is diagnostics and the least agreed upon strategy is pernicious execution. We also showed several comments on why practitioners agreed, disagreed, or remain neutral about the identified strategies. Thank you, everyone. If you have any question, please feel free to reach out to me. Have a great conference.
Thank you for your presentation, Farzana. There are no questions in the chat, but I have some. Now we are seeing like the the rest. So you can stop sharing screen or go back to your presentation. I think it's better. My question, well, I have many, but I mean, I read in your paper that you admit an internal threat of validity, right? And you did like a testing of the questionnaire, of the of the questionnaire with the volunteer, right? Um, but I was thinking, to what extent do you think you can extend your findings to the whole community? Because I am not too sure how you recruit people. I mean, it was an invitation to a set of people, and I mean, to what
Mm.
extent this sample is something we can use to
So
generalize your
as we
findings?
as we said, we reached two different kinds of participants. Some are from the university, who is who participated in competitions like capture the flag. So
Hmm.
they are mostly students. And then we also tried to contact people who are practitioners who actually work in the industry. So we
Hmm.
think by this we make sure that we have different kinds of people, different kinds of practitioners who responded in the survey.
Hmm. But what is the percentage of these practitioners versus the student population in the sample?
The student there was for the students we reach out to 30, and for practitioners we reach out to 70, and then there was total 51 participants who were
24 then.
respondent. Yes,
Yeah.
and we
So it's half and a half, half and a half.
yes.
And do you have differences among these two groups? Because initially in my mind it could be.
I actually don't remember that because we didn't differentiate between the students and practitioners' perceptions. We just assume that they all are expert in software engineering. We did notice that there are at least the median experience in vulnerability discovery was at least 2 years.
Hmm. Yeah, yeah. I mean, maybe this is for another paper. You are writing it right now, right? And you don't want to tell me, and I respect that because paper engineering is a topic. Is a topic. Okay, so more things on that. I mean, to what extent do you think this again? I mean, is the thing that is in my mind all the time is whenever you have a DevOps or DevSecOps approach, all these vulnerabilities will, and the need to discover them will be lesser than a previous approach in which automatization is not this important.
Sorry, what was the question?
The question is, to what extent do you think DevSecOps or SecDevOps will alleviate the problem of the vulnerability discovery?
According to the respondent, we think that like the strategy diagnostic can be really useful. There was some confusions or some questions whether like malicious payload construction can be as important as the other one. But overall, yeah, we believe that all these four strategies could be really helpful to
Hmm.
identify the vulnerabilities.
Hmm.
This
And
is based on the respondent surveys.
hmm. Another question, because this is something that is for the ones that are devoting our lives to education plus research, but also education. To what extent do you think? I mean, maybe it's not there, but that the formal training in vulnerability detection in the university, both in bachelor or master level, will help the overall level in the topic.
Yeah, we did see when we were working on this, we did see that people have asked for this type of questions like what type of uh, strategies are there to find the latent vulnerabilities. So yeah, training the students or the practitioners at the early stage could be really helpful, and we think that yeah, our work practitioners in identifying the software vulnerabilities by training them properly.
Hmm. But do you think it's better train them at the same time that you train them to program? Well, so all this programming first, so security first, or
No,
security
we
last,
think
or how?
we think that security should be included while programming.
Hmm.
Otherwise, otherwise it won't work as effectively.
Yeah, because there was a traditional, let's say, discussion on computer science teaching. They say, okay, should we train students to program first, or first, I don't know, analysis,
Yeah.
design plus whatever?
I
And
believe security is as important as programming now. So
hmm,
they
and then
bridge.
security first, then security left, and security first, right?
Yeah,
This is your approach. Well, I think this is a very relevant topic for both the conference and also for this um, workshop. And if there are no more questions, I think I will leave floor for a small, let's say, time to rest. I think the next we will have a break. I think until 11:30. I think. Sorry. No, until 1 o'clock, right? Central European time. Sorry, I was looking at the wrong place. Again, we will have a break, a small break, 9 minutes from now until 1 o'clock Central European time. So thanks for attending, and this will be the end of my session. Thanks for your presentation, and see you in some minutes.